Life. An unbelievable, perfect combination of elements that is able to create living matter. Maybe the biggest mystery of nature. Is life an amazing phenomenon exclusive to our planet? In recent years, we have made several amazing discoveries that suggest that the conditions in our solar system for life might be more prevalent than ever imagined. Recent missions are revealing strange worlds, moons that could have vast oceans concealed beneath miles of ice, like Europa, which orbits around the giant Jupiter. Places where jets erupt hundreds of miles into space, like Enceladus, the tiny Saturn's moon. Or moons with a very Earth-like landscape, with mountains, valleys, clouds, and lakes of liquid methane or ethane, like Titan, the largest moon of Saturn. If life was ever possible, or is now a fact in any of those remote worlds in our solar system, with very harsh and different conditions from Earth, that could imply that life could be possible in any other remote world in outer space.
Second genesis within the same solar system implies that life, the origin of life, is a likely event. If it happens twice in the same solar system, it's likely happening everywhere in the universe.
Now, scientists are searching for planets far beyond the boundaries of our solar system, where we might detect life in the near future. Thanks to the NASA Space Telescope, Kepler, launched in 2009, we know that in our galaxy alone, there are billions of Earth-like exoplanets orbiting their stars. Given the vastness of the universe, with more than 100 billion galaxies, it is hard to conceive that somewhere there is no Earth-like planet that can harbor life.
Unless something very unusual happened here on Earth, then life is developed on thousands of millions of planets just in our galaxy, right? If it's not a miracle, then it's all over the place. That's the bottom line.
In recent years, thanks to Kepler, we have confirmed dozens of Earth-like exoplanets that might harbor life, and even intelligent life waiting to be discovered. We don't know if the discovery of life will happen first on one of these moons or planets in our solar system, or on an Earth-like exoplanet. But what we do know is that we are closer than ever to unveiling one of the greatest mysteries of nature, whether there is life in outer space. Is there life beyond Earth? Humankind has always asked itself this question, but no answer has yet been found. It appears that we are closer to solving this mystery. Recent discoveries have uncovered planets beyond our solar system that are believed to be similar in many ways to Earth.
If I got to ride on a spaceship to one planet that we found with Kepler, the one that I would go to is Kepler 186f. It's one of the smallest ones. It's at the right temperature that liquid water could exist on its surface.
Kepler 186f is the first validated Earth-sized planet to orbit a distant star in the habitable zone where liquid water might pool on the planet's surface. The discovery of Kepler 186f confirms that Earth-sized planets exist in the habitable zones of other stars and signals a significant step closer to finding a world similar to Earth. Kepler 186f orbits its star once every 130 days and receives 1/3 the energy that the Earth does from the Sun, placing it near the outer edge of the habitable zone. If you could stand on the surface of Kepler 186f, the brightness of its star at high noon would appear as bright as our Sun is about an hour before sunset on Earth.
Today, when we take a look at what we know about the origins of life on this planet, it leads us to think that the same things that happened here might well have happened elsewhere. And so life beyond this planet is quite plausible in terms of the science that we know today.
We now know there are 4 important candidates in our solar system to harbor life: Mars, Jupiter's moon Europa, and Saturn's moons Titan and Enceladus. On every of them, we can find all of the 3 key ingredients for life: organic compounds, a liquid, and an energy source.
There is water on Mars under the form of ice at the poles and under the surface, but it is also flowing from time to time at the surface during spring and summer.
Although there's no evidence of any form of life on Mars yet, scientists think it might be found soon. On Jupiter's moon Europa, 2 of those key ingredients can also be found.
We do know there is water on Europa. On the surface of Europa, we have an icy crust. This icy crust has been observed using Voyager spacecraft, but also the Galilean spacecraft in the 90s.
Under an eerie water-ice crust, 10 to 30 kilometers thick, that covers this tiny moon, there's supposed to be a liquid ocean, which may be about 100 kilometers deep. The Saturn's moons Titan and Enceladus have become the search for life priority top spots in the recent years.
Titan is the only moon in the solar system that is known to have an atmosphere. It's also the only place in the solar system that has an atmosphere made primarily of nitrogen, except for the Earth. So Titan and Earth are closely linked in that way.
Titan is a fascinating world. It's the most alien place in the solar system, so to speak, because it, in fact, other than the Earth, is the only place we know of that has seas of liquid on its surface, but those seas are not made of water. They're made of liquid methane and liquid ethane.
Titan is the only place in the solar system outside Earth where there are stable bodies of surface liquid. But at -180 degrees Celsius, this liquid can't be water. We know there are lakes filled with super-chilled liquid methane and ethane. In recent years, Enceladus, a tiny moon orbiting Saturn, has become one of the main goals for exobiology. Enceladus is a small icy moon, quite similar to Europa, as it has a thick icy crust and an ocean beneath. We know there are vast jets of water ice erupting several miles into space.
Enceladus is one of the most interesting places in the solar system because of the presence of this activity, this geyser-like activity. If we have geyser-like activity, people expect to have water, liquid water.
Recently, in those jets, some of the basic chemical building blocks of life have been detected, so we can be sure that we have on Enceladus the trifecta to harbor life: liquid, organic compounds, and an energy source. But if life was able to emerge in any of those remote and harsh worlds, why couldn't it also arise on any other planet far beyond the boundaries of our solar system?
The second genesis within the same solar system implies that life, the origin of life, is a likely event. If it happens twice in the same solar system, it's likely happening everywhere in the universe.
If we were able to find life within our own solar system on another place, and furthermore, be able to say that it developed, independently, then you're saying within the same stellar system, you had life evolve twice. And the conclusion from that is that life forms very easily.
A generation ago, just the idea of a planet orbiting a distant star was still in the realm of science fiction. So, to think of the possibility of life on a planet like that was simply unimaginable. In fact, the first exoplanets weren't discovered till 1992. That very year, 2 super-Earth exoplanets were found around pulsar PSR 1257+12 at a remote distance of 2,300 light-years away. This announcement shocked the scientific community at that time, as it was the first multi-planet extrasolar system ever discovered. Could any of these super-Earth harbor life? Unfortunately, a pulsar is a very different kind of star from the Sun. In fact, it's a dead star, formed when some of the largest stars in the universe exploded as supernovae.
A pulsar, which is what's left after a star, a really massive star explodes, and you've got this thing which is one step away from being a black hole. While this was really exciting, it was hard to tell what it meant because pulsars are so much different from normal stars.
These may not seem at first to be good places to look for habitable planets. Supernovae are, frankly, quite apocalyptic events that would easily vaporize any ill-fated planets in orbit around the exploding star. That distant world would be bathed in a lethal cocktail of X-rays and charged particles emitted by a star so faint in visible light that it would scarcely cast a shadow on this world's surface. So the chances of life arising in such a weird and hostile environment would be remote. However, the real importance of this discovery was that for the first time ever, the existence of planetary systems beyond the limits of our solar system was confirmed. If we found 2 exoplanets out there, why couldn't there be many more? We had to wait 3 more years to find an exoplanet orbiting a Sun-like star, which was far more important because the conditions of such a planet would be potentially similar to any of the planets in the solar system. On October 6, 1995, was the announcement of the discovery of the first planet orbiting a Sun-like star in the journal Nature. That star was 51 Pegasi, a Sun-like star located 51 light-years away, and the exoplanet was a giant planet.
The first exoplanet found around a star like our own was called 51 Pegasi b. It's very unusual. It's a very large planet. It's bigger than Jupiter. It's more massive than Jupiter. And it's on a very short period orbit. It goes around its star. 1 year on this planet takes 4 days. It's a very short amount of time.
That discovery marked a turning point in the search for exoplanets. From that moment on, many new ones were found. Nevertheless, what radically revolutionized the search for exoplanets was the NASA Space Telescope Kepler.
Before Kepler was launched, there was hundreds of planets that we knew of in systems around other stars, and now we know of thousands. And that's why Kepler was so revolutionary.
The Kepler was a space telescope specifically designed to survey our region of the Milky Way galaxy to discover hundreds of Earth-sized and smaller planets in or near the habitable zone of their respective stars and determine the fraction of the hundreds of billions of stars in our galaxy that might have such planets.
It works very simply. I mean, anybody can understand this. It's just staring at one spot on the sky all the time, never blinks. And it's looking at 150,000 stars. And it just monitors how bright they are, kind of like a camera light meter, really. And occasionally they'll see this star over here, for example. It'll get a little bit dimmer, a very fraction of a percent dimmer for a few hours, and then it'll get bright again. Well, that happens if a planet passes in front of that star.
We've gone from finding 100 planets to over 1,000 planets with Kepler, those that have been confirmed. And there's about 3,000 or 4,000 more which we have strong evidence for, but we wouldn't consider confirmed planets just yet.
Kepler is on the hunt for planets. Kepler has found literally thousands of planets or planetary candidates. It's a planet-finding machine.
In 2011, for the first time ever, Kepler provided scientists with a census of the Milky Way, so we could calculate how many stars in the Milky Way could have a planet like ours. Around 1 billion.
Maybe there are 1 million, maybe there are 1 billion, maybe there are 100 billion planets in the Milky Way galaxy that could support life, the kind of planets that earthly life could survive on. How many of them have cooked up their own life? And we don't know the answer to that, okay? Because that depends on how hard it is to get life started. Just because I give you all these, these worlds doesn't mean that life will get started. But on the other hand, those planets are all made out of the same stuff that Earth is. So again, unless something very unusual happened here and nowhere else, there's going to be biology all over the place.
Just 4 years after its launch, on April 2013, the Kepler team reported one of their first great triumphs, the discovery, for the first time ever, of 2 exoplanets very similar to the Earth, Kepler 62e and Kepler 62f. This discovery created great enthusiasm, as it implied the confirmation of Earth-like planets where life might be possible. Each of these planets have a radius 1.6 and 1.4 times of Earth, and orbits Kepler-62, an orange dwarf star, in its circumstellar habitable zone. A modeling study also concluded that Kepler-62e and Kepler-62f are likely covered mostly, perhaps completely, in water. Kepler-62e probably has a very cloudy sky and is warm and humid all the way to the polar regions. Kepler-62f would be cooler, but still potentially life-friendly. Unfortunately, they are at a huge distance of 1,200 light-years away in the constellation of Lyra. Thanks to the Kepler mission, we now know that there are tens of billions of planets orbiting stars just in our galaxy, the Milky Way, and we know there are billions of galaxies across the universe. So if in just one planetary system like ours, life arose on one planet, and there are at least 4 more candidates, the likelihood of finding a planet in outer space that could harbor life should be very high. But Kepler has discovered for us not only the existence of Earth-like planets, but also has provided us with amazing data about the universe, such as the confirmation of the existence of planets that orbit around not only 1, but 2 stars, like Kepler-16b. This planet was Kepler's first discovery of a planet that orbits 2 stars, what is known as a circumbinary planet.
So one of the most exciting discoveries from Kepler was that we were actually able to find planets around binary stars. And the first one that was found was Kepler-16b.
Kepler-16b is many people's favorite planet that was discovered with Kepler. It orbits around not 1, but 2 stars at the same time. This was something which was predicted not to exist. 2 stars setting at the same time was just a piece of science fiction. But the universe is stranger than what scientists can imagine, and it turns out that this sort of thing is true.
Since 1992, over 2,000 exoplanets have been discovered. Thanks to future Space Telescope missions planned for launch, the number of observed exoplanets is expected to increase greatly in the coming years. Despite having discovered just a tiny fraction of all of those billions of exoplanets that we think that exist, how could we know how many of them could harbor life? In astronomy and astrobiology, the region around a star where a planet with sufficient atmospheric pressure can maintain liquid water on its surface is known as the circumstellar habitable zone.
The habitable zone is a place, it's kind of a way of thinking about the right way to go look for planets like our own.
The Earth is obviously in the circumstellar habitable zone of our solar system. A potentially habitable planet implies a terrestrial planet with conditions roughly comparable to those of Earth, and thus potentially favorable to life.
There's a sweet spot, an area where it's not too hot and not too cold, and we call that the habitable zone, or some people call that the Goldilocks zone. If you've got a planet in that regime, and if it's small, if it's rocky enough, and it had water, that water would be in a liquid state, more than likely. So that would be a good place to go looking.
On November 2013, astronomers reported, based on Kepler space mission data, that there could be as many as 40 billion Earth-sized planets orbiting in the habitable zones of sun-like stars and red dwarfs just in our galaxy, the Milky Way, 11 billion of which may be orbiting sun-like stars. Those 11 billion exoplanets orbiting stars like our Sun really are a huge number of potential Earth-like worlds. However, now we know that stars very different from our Sun may be a good place to look for life. In May 2016, a team of astronomers announced, for the first time ever, the finding of 3 habitable planets orbiting a star completely different from ours, an ultra-cool dwarf star. It's the first planetary system found around a star like this. The star, named TRAPPIST-1, is just 40 light-years away and is much cooler and redder than the Sun, and barely larger than Jupiter. In fact, stars like this are very common in the Milky Way, and they are very long-lived. The 3 planets are very similar in size to the Earth and might have habitable regions on their surfaces. So the answer to what the best place in the universe is to find life nowadays has radically changed. To date, among all of the more than 1,000 confirmed exoplanets, there are around 50 that are in the circumstellar habitable zone of the star they orbit around. And therefore, they could be potentially considered Earth-like planets, which does not imply these distant worlds may harbor life. However, could life be possible outside those habitable zones? The discovery of hydrocarbon lakes on Saturn's moon Titan has begun to call into question the carbon chauvinism that underpins circumstellar habitable zone theory. Liquid water environments have been found to exist in the absence of atmospheric pressure and at temperatures outside the circumstellar habitable zone temperature range.
Just because a planet is outside the habitable zone doesn't mean that it couldn't have life.
For example, Saturn's moon Enceladus and Jupiter's Europa, both outside the habitable zone of our solar system, may hold large volumes of liquid water in subsurface oceans. If we are considering the possibility that life could arise in such harsh environments, which are not in the circumstellar habitable zone, that implies that we should look for exoplanets far beyond those zones. So the chances of finding an exoplanet with conditions to support life are much higher. We know that it's not an easy task to study and analyze the planets and moons of our own solar system, as they are millions of kilometers away from Earth. However, exoplanets are not just millions of kilometers away, but many light years away from Earth. How can astronomers manage to study exoplanets if they are trillions of kilometers away? There are several methods used by astronomers and astrobiologists to discover and to study these extremely distant, mysterious worlds. Before the launching of the Kepler mission in 2009, the most successful technique for detecting exoplanets was the Doppler spectroscopy, also known as the radial velocity method. The radial velocity method relies on the fact that a star does not remain completely stationary when it is orbited by a planet. A planet is much smaller than its star, but it still exerts a tiny gravitational pull or tug on the star as it orbits. When a planet is behind the star, from our point of view, it pulls the star slightly away from us. When it's in front, it pulls the star slightly toward us. This causes the star to wobble back and forth. Astronomers look for this wobbling to find planets. They use something called a spectrograph and powerful telescopes to examine the light coming from a star. A spectrograph, like a prism, splits the light from the star into its component colors, producing a spectrum. Some of the starlight gets absorbed as it passes through the star's atmosphere, and this produces small, dark gaps or lines in the spectrum. As the star moves closer to us, these lines shift toward the blue end of the spectrum. As the star moves away, the lines shift back toward the red end of the spectrum. So the spectrum appears first slightly blue shifted and then slightly red shifted. Therefore, astronomers can look for orbiting planets by looking for these back and forth motions of the lines in a star's spectrum.
And you can work out from the speed that's being pulled towards you and how long it takes to go around in that circle, you can work out the mass of the planet or the companion thing which is pulling it around. If that mass is very small, the thing is a planet. That method has been very successful. It found most of the planets which were discovered early on.
However, the Kepler technique was based on the planet's transit. The transit method is based on the observation of a star's small drop in brightness that occurs when the orbit of one of the star's planets passes. Transits in front of the star. The amount of light lost depends on the sizes of the star and the planet, and the duration of the transit depends on the planet's distance from the star and the star's mass.
With the Kepler Space Telescope, when we look at a star, we don't see the planet directly. All we see is a tiny dip in the brightness of the star when the planet passes in front of it. From the size of the dip, we can work out the relative size of the planet. Is it a big planet or is it a small planet?
The combination of transit photometry and Doppler velocimetry reveals planetary radius, mass, and density, which are some of the main parameters to evaluate the potentiality of the exoplanet as an Earth-like candidate, and so to harbor life.
Once you know the distance away from the star and you know how hot the star is, you can estimate what the temperature on the surface of the planet would be like.
Another of the main parameters to analyze the Earth-like potential of an exoplanet is its atmospheric composition. Atmospheric studies of exoplanets might be performed with spectroscopy during planetary transits. During the transit, the stellar light passes through the atmospheric limb of the planet. Spectral analysis of this filtered light reveals the structure and composition of the atmosphere. Astronomers could identify the most Earth-like exoplanets by detecting the biomarkers, which are the imprints that life forms have on their host planet atmosphere. For instance, the molecular oxygen that we are breathing results from the presence of life on Earth. Unfortunately, with present-day technology, it's extremely hard to closely study the atmospheric composition of those remote planets.
The main thing that's keeping us from being able to do that now, of course, is technology. We don't have the technology, in functioning instruments at the moment to be able to do that effectively. But that's something that will change with other missions in the pipeline, like Jack Webb Space Telescope and other missions that are happening.
Kepler continuously monitors over 100,000 stars similar to our Sun for brightness changes produced by planetary transits. Thanks to this ingenious technique, Kepler has confirmed to date more than 1,000 exoplanets. Scientists think that about a few dozen of them can be labeled as Earth-like. Considering the possibilities of finding an Earth-like exoplanet are much higher in the circumstellar habitable zone of its planetary system, the planet hunting then started to focus on those areas. One of the first discoveries was 70 Virginius b, an exoplanet located approximately 60 light-years away in the constellation of Virgo. 70 Virginius b was located exactly in the middle of the circumstellar habitable zone of its planetary system, so it was supposed not to be too hot or too cold. Unfortunately, further studies reported that this remote world was a gas giant with very high temperatures, which ruled out any potential for liquid water and therefore of life. The early findings were discouraging in terms of detecting an Earth analog. But this was just the beginning. In 1998, a discovery made in the star Gliese 876, a red dwarf located in the constellation of Aquarius at a distance of 15 light-years away from Earth, really encouraged astronomers. A gas giant was detected in its habitable zone, Gliese 876b. Three years later, another gas giant closer to this one was found, Gliese 876c. We know that life as we know it is not possible on gas giant planets such as Jupiter or Saturn. But the big surprise was that both exoplanets may have habitable moons orbiting around them, as Jupiter and Saturn have.
This was one of the first planets to be discovered in the habitable zone, and people theorized that if it had a moon around it, the moon would be rocky, and the moon would be the right temperature to have liquid water.
Why couldn't any of these hypothetical moons around Gliese 876b and c harbor life, as we hope Jupiter's moon Europa or Saturn's moons Titan and Enceladus might?
So it's an exciting place to think about, and maybe an exciting place to look for in the future.
After the discovery of these exoplanets with potential Earth-like moons, several similar exoplanets with moons orbiting around them were discovered. Maybe on any of those remote moons, life arose in the past, or exists in the present, or might appear in the future. After all these early discoveries, we started to approach to the main goal, to find the most Earth-like world. An Earth analog, also referred to as a twin Earth or Earth-like planet, is a planet or moon with environmental conditions similar to those found on the planet Earth. If life could arise on Earth millions of years ago, and if we look for exoplanets similar to our planet, the chances of finding habitable planets skyrocket. Recent discoveries have uncovered planets that are believed to be similar in many ways to Earth, with relatively high Earth similarity indexes. The size is often thought to be a significant factor, as planets of Earth size are thought more likely to be terrestrial in nature and be capable of retaining an Earth-like atmosphere.
From the point of view of Kepler, a planet is Earth-like if it's small enough that it's probably rocky. It's not a gas giant like Jupiter or Saturn.
But size alone is a poor measure, particularly in terms of habitability, because next to us, there is a planet with a very similar size and mass, Venus, where it is almost impossible for life to arise. There are other criteria to be considered, like the surface gravity or the star size and type.
A planet is Earth-like if it's the right distance away from its star that it's in the habitable zone, that it's not too close that it's too hot and all the water that it would have would boil away, and not so cold that if there was any water on it, it would all freeze to ice.
If we are able to examine all of these parameters of an exoplanet, we would be able to know if it is or not a real twin Earth.
So when we say Earth-like for Kepler, we usually just mean that it's small enough that we think that it's solid enough that you could stand on it, but that doesn't mean that it has an atmosphere or that it has an ocean.
It's also often cited that an Earth analog must be terrestrial. That is, it should possess a planetary surface composed of materials similar to Earth's. The conclusion would be that extrasolar planets, or moons, in the center of its circumstellar habitable zone, the so-called Goldilocks position, with substantial atmospheres, may possess oceans and water clouds like those on Earth. In addition to surface water, a true Earth analog would require a mix of oceans or lakes and areas not covered by water.
We believe that water is essential, but just about everything else you can think about, which is important for life, there seems to be life on the Earth that doesn't need it. There is life that survives without sunlight, there's life that survives without oxygen, there's life that survives deep down underneath the ice in Antarctica.
Unfortunately, with the present technology, we can't properly evaluate most of the parameters like the temperature, the atmospheric composition, or the surface of the exoplanets. Nevertheless, considering we have already discovered hundreds of exoplanets, we can't help but wonder if a real Earth analog has already been discovered. On 18th April 2013, astronomers from the Kepler team announced a discovery that created great expectation. For the first time ever, two very Earth-like exoplanets were found. They were the Kepler 62e and the Kepler 62f. And orbits Kepler 62, an orange dwarf star, in its circumstellar habitable zone. They immediately became prime candidates to host alien life. A modeling study also concluded that Kepler 62e and Kepler 62f are likely covered mostly, perhaps completely, in water. Kepler 62e probably has a very cloudy sky and is warm and humid all the way to the polar regions. Kepler 62f would be cooler, but still potentially life-friendly. Unfortunately, they are at a huge distance of 1,200 light-years away in the constellation of Lyra. Soon after, it was discovered an exoplanet even more similar to Earth, Kepler 186f. This finding was a milestone, as it was the first rocky planet found in the habitable zone of its system. It is 492 light-years away from the Earth.
Kepler 186f is possibly my favorite planet to come out of the Kepler mission. It's a small planet. It's maybe 10 to 20% bigger than the Earth. Based on everything we know about planets, it's almost certainly to be rocky. And it's the right distance away from its parent star that, if the atmosphere is right, if the greenhouse effect is right, it could have liquid water on the surface.
After that discovery, several more Earth-like candidates started to arise, like Kepler 438b. Kepler 442b, or Kepler 440b. All of them were very similar to our planet, but none of them was a real twin Earth. But everything changed on July 23, 2015. That day, NASA's Kepler Space Telescope science team shocked the scientific community with an amazing finding. The most Earth-like planet ever was discovered. Its name, Kepler 452b. What made different this one to the other previous Earth analog candidates? Kepler 452b is the very first, apparently rocky planet that orbits a G-type star like our Sun.
It's a planet in the habitable zone around a star which is almost a clone of our own Sun.
After this discovery, the Earth is a little less lonely in the universe. Kepler 452b circles its star, which is about as hot as our Sun, 10% brighter and 20% larger, at an orbital radius just 5% larger than that of the Earth. A year on this planet is 385 Earth days long, just 20 days longer than Earth's.
What makes this slightly less exciting from the point of view as could it be habitable is its size. Our best guess at the size is that it's about 60% bigger than our own Earth.
It is the smallest Earth analog planet ever found in the habitable zone of a G-type star like our Sun. Previous research on super Earth-sized planets like 452b suggests this one has a good chance of being rocky. If it is a rocky world, it'd weigh in at about 5 Earth masses, giving it a surface gravity of roughly 2 grams, which would mean that our weight would be double on its surface. Kepler 452b could have a thick, cloudy atmosphere and volcanic activity. Even more exciting than Kepler 452b's Earth-like demeanor is the fact that this world has spent around 6 billion years in the habitable zone of its star. That's considerable time for life to arise somewhere on its surface or in its oceans, should the conditions for life exist. Kepler 452b is about 1.5 billion years older than the Earth. If it was Earth-sized, the planet and its aging, brightening star might be at a point in their evolution where liquid water would be rapidly evaporating from the surface. But because of its higher mass, astronomers believe Kepler 452b could continue to hold liquid water for the next 500 million years or so. So far, it's the only known world in the system, which lies some 1,400 light-years away in the Cygnus constellation. Obviously, we're not going to get there anytime soon, but it's fascinating to imagine that far off in the distant reaches of space, a world very much like our own might already exist. If this twin Earth exists, why couldn't thousands more like it exist? Less than a year after the amazing finding of Kepler 452b, on May 2016, a new discovery shocked the scientific community. Astronomers using telescopes at European Southern Observatory in Chile discovered 3 planets around a dim dwarf star just 40 light-years from Earth in the constellation of Aquarius. These worlds may be the best targets so far found in the hunt for life elsewhere in the universe. They used the TRAPPIST telescope to monitor the brightness of an ultra-cool dwarf star in the constellation of Aquarius, which has been named TRAPPIST-1. TRAPPIST-1 is much cooler and redder than the Sun and barely larger than Jupiter. Stars like this are very common in the Milky Way, and they are very long-lived. this was the first time that planets have been found around one of them. The 3 planets are very similar in size to the Earth and might have habitable regions on their surfaces. But the really exciting result is that these are the first Earth-like planets that are well suited for the detection of life. The ultra-cool dwarf stars are the only places where life could be detected on an Earth-sized exoplanet using our current technology. The light from much brighter star, like the Sun for example, would swamp vital measurements of the atmospheres of any candidate planets. The next step is to make more detailed observations using the next generation of telescopes, such as ESOs, European Extremely Large Telescope, and the James Webb Space Telescope. That will allow astronomers to study the atmospheres of planets like this and to search for molecules related to biological activity, like ozone, methane, or water. Although there is not yet any proof of the existence of life on all of these exoplanets that we've already found, even in the most Earth-like of them, like Kepler 452b, we can't help but wonder if any of those potential forms of life that might have arisen there were or will be able to evolve into intelligent life. If any of those extremely remote worlds was formed billions of years ago, as Earth did, and it became into a habitable planet, then the organic compound had time enough to mix up and organize into living forms. Perhaps any of those living forms might have evolved into complex forms of life, and some of those complex forms of life might evolve into intelligent beings with consciousness. Thanks to Kepler mission research, it's known that just in our galaxy, the Milky Way, there might be millions of Earth analogs, and there are billions of galaxies across the universe. So the chances are much higher than we could have ever imagined. For that reason, science is carrying out an intense search for intelligent life. The SETI Institute in California is nowadays the main world institution devoted to the search for extraterrestrial intelligence. Its name, SETI, stands for Search for Extraterrestrial Intelligence. This search is based on the use of radio telescopes. Radio telescopes receive radio waves. As we can't go to space aboard spacecrafts to find that intelligent life, what we look for are radio signals.
What we're looking for is a signal that's at one spot on the radio dial. Just like when you're listening to the radio in your car. You know, you tune across the dial, you hear static everywhere, and then at one spot you're near, and there's a station. Okay, that's the signal that's produced by a transmitter somewhere. It's not natural static. It's not like a quasar or a pulsar or galaxies or hot gas, cold gas. All those things in space make radio noise, but it's all over the dial. So we look for signals that are at one spot on the dial, and of course the source of the signal has to be up in the sky. Those are the kinds of criteria we use to know that even if we don't know what it means, we at least know they're there. They're on the air.
Unfortunately, till now, we haven't received a signal that can be really attributed to extraterrestrial intelligence. In the coming years, NASA and ESA, the European Space Agency, have planned to launch several space telescopes that will surely help to unveil the mystery of life beyond the boundaries of our solar system. The most ambitious one is the James Webb Space Telescope. This project is an international collaboration between NASA, ESA, and the Canadian Space Agency, CSA. It will be the premier observatory of the next decade, serving thousands of astronomers worldwide. It will study every phase in the history of our universe, ranging from the first luminous glows after the Big Bang to the formation of solar systems capable of supporting life on planets like Earth, to the evolution of our own solar system. This new telescope, 3 times more powerful than Hubble, will be able to analyze starlight passing through the atmospheres of the closest Earth-like worlds, looking for the telltale signs of life itself, like, for instance, detecting gases in its atmosphere usually linked to life processes such as oxygen, methane, carbon dioxide, or nitrogen.
JWST is really going to help us understand what atmospheres of planets are like under different conditions, and that's going to be a really exciting result.
There is another mission, the CHEOPS mission. CHEOPS comes from characterizing exoplanet satellite. This is an ESA mission dedicated to searching for exoplanetary transits by performing ultra-high precision photometry on bright stars already known to host planets. With all of these new space telescopes programmed to be launched in the coming years, we are sure that finding a habitable exoplanet and any consistent biosignature will be just a matter of time. If we are ever able to find evidence of the existence of any form of life among one of those billions of exoplanets we know are across the observable universe, it would be undoubtedly shocking.
If we did find life somewhere else in the solar system and we were able to do, for example, a genetic analysis to determine that it was distinct from life on Earth, that would be a really earth-shaking discovery.
Living generation might be witness of a finding that would undoubtedly be a turning point in the history of humankind. The discovery of life in outer space.